Thanks for watching, and here are all the vector calculus tools that we'll need for our next application, which is about fluid flow. And by the way, here we'll do everything in 2 dimensions, but all this can be generalized to 3 dimensions as well. So, the first concept that we'll need is a vector field. Namely f of xy, which really is a function or a vector with 2 components. With 2 components. So, for instance, you could have f of xy, let's say is x squared plus y squared, and then 3x minus 2y, for instance. And the way to visualize this is, at every point xy, you have a vector. Maybe this is f of xy, or maybe at this point you have another vector, at this point you have another vector, etc., etc. So, in the end, you get a bunch of vectors, and that's what's called a vector field. Now, the next concept that we'll need is the unit normal vector. So as I said, concept 2 is what's called the outward facing unit normal vector. Which we'll call n. So in this case, suppose you have a 2D region omega, and with boundary curve, partial omega, then at every point you have a vector of length 1 that's outward facing and perpendicular to that curve. And that's what's called the outward facing unit normal vector. Just like that. And this vector allows us to define what's called the net flux. So not Netflix, but net flux. And what the net flux is the amount of fluid that goes out of the surface. So let me explain. Now, the next concept that we'll need is the one of a net flux. Again, not Netflix, but net flux. And I want to motivate this with a little example. So suppose you have, again, your region omega with boundary partial omega. And this time, assume your vector field flows outwards. So it might look something like that. Maybe like this. Then we would expect the net flux to be positive, because the net flux, what it measures is the amount of F that either flows in or flows out of our surface. So without further ado, here's a definition. So the net flux, which is again the integral of F dotted with ds, all this is you take F dotted with the unit normal vector and you integrate that over that curve in this case. So this little ds, it indicates line integral. Although in 3 dimensions, you would do a surface integral. So what does that mean concretely? So you take F, you dot it with the vector n, which gives you a number. So in this particular example, it's a positive number. And you do this for every point, maybe like this. And you just integrate this on the surface. You sum up the values of the point that you got. Because this is ds, and then just take the sum, and it gives you a number which, again, represents the total amount of fluid going in or out of that surface. So, yes. So this represents the total number of fluid going in or out of your boundary. Things like amount of water that goes in and out. So here, the net flux F dot over ds is positive. And related to the amount of fluid going in and out is the concept of the divergence, which I'll talk about now. So the divergence also measures how much a fluid spreads out. More precisely, it has a following definition. So divergence. So the divergence of F is just the divergence. Let's say F has components P and Q. And what it is just Px plus Qy. So you take the x derivative of the first component, the y derivative of the second component, and you add them up. So just as a very quick example, the divergence of, let's say, 2x minus y, and then let's say 3x squared plus 5y squared. So once again, you take the x derivative of the first component and the y derivative of the second component, and what you end up getting is 2 plus 10y. And once again, the interpretation is that the divergence measures the spread of the vector field. Measures the spread, or literally the divergence of F. For instance, if you have a vector field as follows, where it just goes out like that, then we would expect that the divergence is positive. On the other hand, if your vector field rotates, then the divergence should be 0, because it doesn't spread out. And now we have learned two concepts. One is the divergence, the other one is a net flux. The cool thing is they are related with what's called the divergence theorem. So what is the divergence theorem? Also called the Gauss-Green theorem. So they're two important mathematicians, hence it's an important theorem. And what this tells you is that if you take the net flux, so F dotted with ds, that's the same thing as the integral over the whole region of the divergence, F dx. So here in this case, it becomes a double integral. Now, let me explain what this means. So once again, in this case, suppose you have your region omega with the boundary partial omega. Now remember, the divergence measures how much F spreads inside. So at every point, you're adding those little arrows. So that would be the divergence of F. So once again, in your region, you're adding up the divergences. This is the same thing as figuring out how much goes in and out of the boundary. So it turns out that's the same thing as the net flux, which once again, you're on the surface, you're adding F dotted with those normal vectors, and you're just adding it up on the surface. In other words, if you want to measure how much water is going in and out, there's two ways of doing it. Either look at the boundary, how much water is going in and out, or look inside and see how much the water spreads. And this is saying that we're actually measuring the same thing. Last but not least is the concept of a fluid flow, which is a very nice differential equation. Now, the final concept is the one of a fluid flow. And what this is simply a differential equation. So let me motivate this with a picture first. So suppose you have a vector field F. Think of it as a wind, if you want. Then what you can do, you can start with a point and just follow that wind. In other words, the flow X is simply a curve whose derivative is the given vector field. So in other words, start at the point and literally just go with the vector field F. So more precisely, definition, given a vector field F, the flow of F is the ODE x prime of t equals f of x of t. In other words, the curve x, whose derivative is precisely the vector field f. So x of t is the curve whose tangent, so derivative, or tangent vector, is f. And so really, just as a concrete example, if, in this case, f of xy is, for instance, 2x plus 3y, and then x squared plus y squared, then the flow is x of t, which is, again, the vector with components x and y, whose solution, or which solves, in this case, x prime of t is 2x of t plus 3y of t, and then y prime of t is x of t squared plus y of t squared. So again, it's the function whose derivative is precisely the vector field f, which is very, very cool. All right, now those are all the tools we'll need for our next application, which is fluid flow. So now in the next video in the playlist, you can finally see how we can apply this. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.